Okay. Question 5 says, give a careful statement of a theorem from lecture about the halting problem for racket programs. So, halting prob for racket programs. That just says progs. I think if you remember from class, this is basically the idea that we can't determine whether every single possible function you input to something will terminate. So we cannot have a function halts prod expression that returns true if prod expr halts and false, this is a T, if prod expr does not halt. Basically says this is impossible is the theorem. I might have messed up some wording, but I think this is the general idea. I will move on to 5b. Just me to give an example of the cd command in Linux and briefly explain what it does. So I'll say cd changes my working /current directory. And then an example would be something like if I can ls, and then that returns, like my dir some file.txt cd my, or what's a better, maybe I can come up with a better example. I'll say, before this I'll say pwd, so present working directory, and that will return /home, or like what about, actually no, what is with it, I don't know, something like ~users /lrc42, something like that. ls, here's my dir, cd, my dir. This won't return anything, but then I can write pwd, and it'll say users, this is a tilde, users lic42 my dir. Okay, I think that's an example of how to use cd. That's sufficient. And I've explained briefly what it does. You might want to know, like, these things out here will also change. It usually says basically where your working directory is. So if I wanted to be super complete and be really careful, I could write here my working directories and show that that changes after I cd. But I'm not going to do that right now. So that was 5b. Now on to 5c. Is the following procedure tail recursive? I'll write it out really quick. It says define our length. I know my handwriting is getting progressively worse. It started pretty bad, but I'm sorry if you can't read what I'm writing. If in a list 0 plus 1, our length cdr_lst. Okay, it says, is this tail recursive? Whenever I see this +1, the answer is no. So tail recursive means that we keep track of our answer as we go, and when we finish, we can just output that answer. This is going to build up a tree of calls that's like +1, +1, +1, +1, 0. This is just not tail recursive. Make sure you know what the definition of tail recursive is, and that you're able to just say no. And do I have to explain? It says why or why not. So this is not tail recursive. I don't know exactly how to explain it. They might be looking for something in particular, but I would probably say something like, because after the last recursive call, the operations stored in memory on the return of that call still need to be executed. I think that explains basically why this makes it not tail recursive. Probably not the most elegant explanation, but I think this would probably get the points. And then 5D asks me to draw another tree of recursive calls, so I'll erase this. For the application rep true to, the procedure rep is defined as follows. So basically we have to figure out what this procedure does, and I'll write it out really quickly. Maybe I'll do it over here so I have space. Define rep value n if equal n0 list value, and else list rep value minus n1 rep value minus n1. All right, so looks like, if I give this, just so we understand what this does, is I think if I give it something like the value, say 3, rep value, or I have to give 2 inputs, like rep 3, and I'll say n is 2, it'll say, so n is not 0 yet, so rep value minus n1, and I'll have 2 copies of this, so I'll say like rep 3, 1, and then list that with another copy of rep 3, not list 1, rep 3, 1. These will get listed together. And then here it's still not 0, so this will say rep 3, 0, list that with rep 3, 0. And that will get listed together with list rep 3, 0, rep 3, 0, lots of parentheses. And each of these won't recurse, these will just return 3, 3, 3, 3. So it returns like 2 to the n copies of value in a list. We didn't have to write this out or figure it out. I think it's helpful for just visualizing and thinking about the recursive calls. So I'll erase this really quick and write the actual thing we have to draw the tree of recursive calls for. It's rep true to, so rep 2. This will call, because n is not 0, list on rep true 1, rep, wow, this is going to be long, rep true 1. These will each call list rep true 0, rep true 0, list rep true 0, rep t0. And then these don't make a recursive call, so this is my tree of recursive calls without return values. Oh, I think I might have messed up. So it doesn't actually return just those numbers in a list. Here it lists the output. So this would return something like, this would return, and then it would list these. So your output list here will actually look like Not that you need to do this, none of this is necessary, you just have to draw the calls, but the output would actually look like not what I said earlier. Okay. Now I'm going to move on. No, I've actually fixed that. Okay, now it says for E, rewrite the special procedure in 5D, or rewrite this procedure in 5D using the special form let to avoid redundant computation. So here it calculates this or runs this function on true and 0 a whole bunch of times, completely unnecessary. We can rewrite this super easily using let to make it more efficient. So basically we're just going to let something equal this, and then we can list that thing twice instead of having to calculate it twice. So a lot will be the same. I'll say define rep value n if equal 0n or n0, whatever. List value, that doesn't change. But then my else is going to say let x be rep value minus n1, and then I'll close these parentheses, or leave one over, yeah, so these correspond to these here, and then I'll say list x instead of list rep value at minus n1, list rep value minus n1. So then I'll close my let, I will close my if, my define. Okay, I think I did that right. Got a little distracted, but if it's 0, list value, else let x be rep value minus n1. This closes this rep value, this closes that, list xx, this closes the let, this closes the if, this closes the define. Okay, I think I did it. Great. And we're on to 6. So make sure you get the parenthesis syntax right for let. I think that's the most confusing part. You might have seen let written with something like let bracket parentheses, like this. Like this will return 5. You don't need to do bracket parenthesis, or parenthesis bracket. But this just helps you see where they kind of line up. Bracket actually doesn't care whether you use brackets or parentheses, as long as they match up correctly. Okay, 6. Evaluate the